Hello, I'm excited to share with you about my PhD research. My name is Erfan Farhikhteh. I'm early stage researcher number 5 in Zephyr project, which is part of European Union's Horizon 2020 Research and Innovation Program. My most recent academic pursuit is my master's degree in Advanced Structural Analysis from Politecnico di Milano in Italy. Currently, I'm doing my PhD in National Technical University of Athens at Parallel Safety and Optimization Unit. In this video, I'll explaining about the project and my research in very simple terms. The title of my PhD is Adjoint-Based Aerodynamic and Aeroacoustic Shape Optimization of Roof and Ground-Mounted Horizontal Axis Wind Turbines in Built Environment. The project primarily focuses on the development of continuous adjoint method and programming on in-house OpenFOAM code, with the objective of optimizing the shape of the rotating objects, such as rotor blades, in order to maximize the aerodynamic performance and reduce emitted noise. One of the most promising sources of green energy is the wind power that is sustainable, clean, and does not produce harmful greenhouse emissions that contribute to global warming. Wind turbines are commonly used to capture the kinetic energy of the wind and convert it to electricity. However, optimizing the performance of wind turbines can be challenging, especially in urban environments where the flow can be uncertain and complex. That's where Zephyr and my research come in. I've developed the continuous adjoint method to optimize aerodynamic shape of wind turbines blade and improve their performance in urban environments. In order to accomplish this task, I've created a specialized adjoint code to take into account the rotation effect of blades. Through the utilization of continuous adjoint method, a powerful mathematical optimization approach that relies on gradient-based methods, I'm able to effectively enhance aerodynamic efficiency of wind turbines blade to produce more energy. In urban environments, flow can be highly uncertain due to various factors. In my research, I've addressed flow uncertainties in urban environments using polynomial Gauss expansion. This innovative mathematical approach allows for more robust and reliable blade designs that perform well under uncertain flow conditions. By incorporating polynomial Gauss expansion into the optimization process, we can create wind turbine blades that are more suited to the urban area. Built-up areas are often plagued by noise pollution, including that from wind turbines. Through my research, I've tackled this issue by conducting aeroacoustic analysis using ambient model with Python code that I developed and performing aeroacoustic shape optimization using the continuous adjoint method coupled with Brodmann model. This approach aims to minimize noise emissions of rotor blades, making them more suitable for urban areas. Secondments can facilitate collaborations between universities and industry, leading to the potential for future research, partnerships, and career opportunities. I did my secondments in University of Twente in Enschede, Netherlands, to familiarize with aeroacoustic formulations. Afterwards, in Institute of Fluid Flow Machinery, Polish Academy of Science in Gdansk, Poland, to assess applicability, noise control technologies, and then in Siemens software in Leuven, Belgium, to get familiar with Siemens software numerical acoustics solver. As I wrap up the video about my PhD journey, I would like to extend my sincere thanks to Parallel Safety and Optimization Unit of NTOA for their invaluable mentorship in adjoint methods and programming, which has greatly contributed to my research. Thanks for tuning in to learn about my PhD project.